Okay, welcome back, everybody. This is it. This is the last lecture of the course, and it's a good one, the divergence theorem. It's a very cool section, a very cool result. It can be generalized to any number of dimensions. Many of you are going to see it in big ways later. It's a good way to end. All right, let me pull up the slides and we will get started. So section 16.9, this one's all about the divergence theorem. Again, this will be relatively short. It's an important theorem, but frankly, the bulk of the chapter has just been leading up to this point. So there's not as much more that we need to say. We just need to kind of finish up and get this lovely result. So kind of similar to the last section, we're going to start with just some development. We'll get the statement of the divergence theorem. We're going to prove the divergence theorem in a nice enough case. We'll do an example, and then we'll clarify divergence at the end just to settle it on a little more, to make it a little bit more formal, just to get an idea for why intuitively it means what it means. And we'll connect that to the mathematics as well. Okay, so here's the development. So if you remember the second form of Green's theorem for planar regions, it looked like this. This was where you basically take the outward normal component of the vector field on the boundary of a region, and that's going to be equal to adding up the divergence of the vector field within the region. That was Green's theorem, right? Here, partial D is the boundary of that region, and it's positively oriented, right? So our goal is to extend this theorem to vector fields on R3 and then later on just in general. So what we're going to do is we're going to make a good guess. In mathematics and science, this is often called an ansatz, basically a good guess at what you think is going to work. And then hopefully it does work. You'll see it in differential equations, for example, when you make a good guess for solutions to those. But we're going to just make a guess that the higher dimensional version of this formula, excuse me, it looks like this. So maybe if we wanted to extend this into the third dimension, what we're really going to say is that the surface integral on the surface boundary of some solid region is equal to the triple integral of the divergence within that region. Pretty good guess, right? Turns out to be the correct guess, but so it's a good one. All right, now, in order to talk about the divergence theorem, we need one last definition. That's just the definition of a simple solid region. So a region E in R3 is called a simple solid region if it is simultaneously of type 1, 2, and 3. So for example, regions that are bounded by ellipsoids or rectangular boxes, those are simple solid regions. And the boundary of those regions are closed surfaces. So that's what we're looking at, right? Now here's the statement of the divergence theorem. It says, let E be a simple solid region, and let S be the boundary surface of that region E, and with positive or outward orientation, right? Let F be a vector field whose component functions are C1 on an open region that contains E. Then we get the result that we expected. Yeah, our good guess turns out to be quite good. Yes, yes, indeed. Okay, so if you remember what I had mentioned earlier on in this chapter, the divergence of a vector field is basically a measure of the tendency of a particle to flow away from that point under the influence of that vector field. It's like stuff wants to flow away or possibly flow into. That was like the intuition for divergence we got earlier. So the divergence theorem is saying that if you want to calculate the flux over a closed boundary surface, that's equivalent to finding the net divergence within the region that's within the contained region. That's the idea. So basically the same thing as the second form of Green's theorem, but higher dimensions. Now, in application, the divergence theorem is kind of like Stokes' theorem in that it gives us the opportunity to integrate over a surface instead of a region, or a region instead of a surface, depending on what might be easier. And it gives us the connection between those two integrals. The other thing, do I say it here? I guess I should have said it here as well. Again, note the similarity to the fundamental theorem of calculus part 2, right? So that theorem said that you can basically evaluate an integral over a region by looking at the boundary, looking at values on the boundary, and this one is saying something similar. So that's what's happening here as well. Okay, let's prove it. Let's prove it. Let's let our vector field F be given in this standard form. Then by the definition of the divergence, it's equal to this sum. And what we're going to say, or I mean, that means that the triple integral of the divergence can be broken apart into three separate triple integrals using linearity of the triple integral. So if I want to compute this triple integral, it's equivalent to computing these separate triple integrals right here. Yes. If n is the outward unit normal vector of our surface S, then the surface integral on the left side of the divergence theorem looks like this. So there's the surface integral. We can write it in terms of ds right here. And then because f has this standard form, we can compute this dot product. And then again, using linearity of the double integral, we can split this up into three separate double integrals, 1, 2, 3. There we go. So we basically have an expression for this surface integral right here, and we have an expression for this triple integral right here, broken up into three pieces. So it suffices for us to prove that these three equations hold, just kind of comparing equations, right? Or comparing terms in those results. So we're going to prove this one. We're going to prove one of them, and I'm going to leave the others as an exercise. Math majors, you may be interested in trying to do the others on your own. The proof is very, very similar. It's basically the same idea. The only difference is now everything is kind of like turned to the side or turned like this. That's basically it. We're going to prove this one. Okay, so here we go. If we're going to prove the last equation, we are going to leverage the fact that E is a simple solid region. And in particular, we're going to use the fact that it can be considered as a type 1 region. Remember, you didn't need to remember the types, but a type 1 region just means that you can integrate between two surfaces that are in terms of x and y, and then integrate, here you go, integrate between two, well, we'll just leave it at that. Leave it at that. Then we're going to integrate between two curves. That's essentially what goes on here. Do I do that? Oh, no, I didn't even do that. Yeah. We'll just leave it at that. We'll leave it at that. So what is D? D is the projection of our region E onto the XY plane. So that's what D is down here. Okay. Now we got to look at the surface of E. Oop, jumping ahead. I'm jumping ahead too far. Sorry. Yeah, jumping ahead. Sorry. So now we can rewrite this triple integral here like so, because we're viewing E as a type 1 region. So now we can basically integrate, we can iterate the integral, and we can integrate between these two surfaces, and then we'll be left with a double integral after that. Now, by FTC2, we can apply it to this, and simple application yields this: R of xy and u2 evaluated at xy minus R of xy and u1 evaluated at x and y, just like that. So hold this equation in your mind, or just hold it on the slides for a minute. We're going to refer back to it. Now let's look at the surfaces that we have to deal with. We've got something for the triple integral. Now let's look at the surfaces of the region E. So the boundary surface itself is actually three pieces right here. There's a bottom surface, S1. There's a top surface, S2. And then there's a sideways surface, a vertical surface, S3, just like I indicated right there. Yeah, and S3 lies above the boundary curve D. So S3 in particular is directly above the boundary curve D. Now, it might actually happen that this surface S3 is not there. For example, in the case of a sphere, S3 basically gets shrunk down to nothing, and you only have the top surface and the bottom surface. So, but not necessarily. So we're just going to assume that we do have a possible S3. And on S3, we can compute this surface integral. So surface integral over S3 is going to be equal to this. But remember that the outward unit normal vector is, oh, I'm sorry, we're dotting it with K, right? We're dotting it with K, which is this vector right here. So the outward unit normal vector on S3 is always going to be orthogonal to the vector k, the basis vector k. So this dot product is going to be 0, and that means that this entire integrand is going to be 0, and so we get 0 as this result. Long story short, the surface integral over S3 ends up being 0. That's it, because the outward unit normal vector is orthogonal to k. All right, so yeah, this means that regardless of whether or not there is a vertical surface, so even if there is a vertical surface, the integral there is going to be 0. If there's not a vertical surface, great, we don't have to worry about it. So now what we can write is that this surface integral is actually the sum of these two surface integrals over S1 and S2. That's where we're at here. Okay, now S2 is the surface given by the equation z equals u2, where x, y are in D, and the outward unit normal vector n points up. So just to go back to the picture, here is S2, right? And the normal vector points up, just like that, okay? Yes. So now what we're going to do is we're going to use that formula once again that I mentioned from section 16.7. It was on slide 41 if you want to go back and look at it. But this time we're going to replace F with RK. So RK is now our F. And what we get after we apply that formula is just this. Just that right there. Just R. R with the z component evaluated on the surface itself. Now we can use the same argument on the surface S1. That's the surface beneath right here. We can use the same argument, but now the outward unit normal vector points down. It's pointing down. So we need to multiply the whole thing by -1. So in this case, n is actually, or sorry, I'm sorry, this will actually end up being -1. And so then what you get is this. There we go. Okay, now we're going to add those together. So we're going to add these together to get this. Now it all connects. Now it all connects. So remember, this surface integral over S was equal to the sum of these two surface integrals right here. And we just found that those are this and this. So when we merge them together, we get this. But this is exactly the same expression we got when we evaluated this triple integral earlier. So now everything's kind of come together, and at last we can say that this is equal to this. There it is. So we did that for one of those three equations. Now the other two equations are solved similarly, and then you combine them all, add them all up again, and then you get the result of the divergence theorem. That if you want to compute this surface integral, you can compute this triple integral of the divergence. Cool stuff. Okay, now this one, I think I might want you to try on your own first. Yeah. Okay, try this one on your own first. Hold on a second here. Let me get some things set up. There we go. Try this one on your own. So see if you can find the flux of the vector field given by this vector field F over the unit sphere. And I want you to do it by employing the divergence theorem. So think about it for a minute. All right. Now, as always, got to say something out loud to give your brain that feedback. So some kind of feedback. Talk to yourself, talk to your friend, talk to your peer, say something out loud. Right, and now try to compute it yourself using the divergence theorem. All right, okay, and now let's work on it together. So first we got to compute the divergence of F. In this case, it happens to be super nice and super easy. Remember, the divergence is just the sum of all those first partials, right? Right there. So you get that, but differentiating this with respect to x gives you 0. This will give you 1. This will give you 0 again. So the divergence in this case is just 1. Now, the unit sphere S is the boundary of the unit ball B given by this inequality. That's the unit ball. So the divergence theorem gives the flux through the unit sphere right here as this triple integral of the divergence. But again, the divergence in this case is just 1. So we're just computing literally the volume of the unit ball, which is 4/3 pi r squared with the radius equal to 1. So we get 4/3 pi. There it is. All right. Okay, next example. So this one, you know what? I bet you could probably do this one on your own too. So maybe try this one. Here we go. Try to evaluate this surface integral where the vector field is given by this function f, and the surface S is the region that you see here, or the boundary of that region that you see here. Okay, so like all this stuff. There you go. That's the surface S, and you want to compute that surface integral. All right? Okay, think about how you're going to do it first. Okay, now say something out loud about how you're going to do it, and then try to compute it. A big hint, use the divergence theorem. Okay, now let's do it together. This is a great opportunity to use the divergence theorem if for no other reason than the fact that you would have to compute 4 separate surface integrals if you wanted to compute the surface integral over this surface. So at least there's that. That's already going to be difficult. You don't want to have to do an integral 4 times, right? The other nice thing about it is that even though that vector function f, that vector field, has pretty complicated component functions, the divergence of that vector field is really, really simple. So just to reiterate or remind you, these are extremely complicated component functions. I mean, you've even got like a tetration going on almost. You've got like a double exponential in there. You've got sine of x times y. Oh man, seems really difficult to integrate. But the divergence cleans up very, very nicely. Look, those partials kind of wipe away all the stuff you don't need, and then you're literally just left with 3y. That's it. So now what you need to do is just compute a triple integral of the function 3y, which may not be too bad. All right, so now you have to make a decision. How do you want to view this region E? Do you want to view it as a type 1, a type 2, a type 3? And this is why we practiced doing triple integrals and things like that back in chapter 15, right? So you have to decide how you want to scan the region. And looking at it in this case, it looks like it would be easier to scan this way first, and then scan between 2 curves, and then scan between 2 numbers. So I would do 2 surfaces in terms of x and z, and then 2 curves, right, in terms of, what is that, z? Yeah, or no, x, yeah, x. Oh yeah, x, yes, x. And then between 2 numbers in terms of x. No, z, yeah, I was right, yeah, z. Like, yeah, between z goes between there and there. There we go. And then x goes between those. So you can do it as a type 3 region. That's what type this is. Okay, that's not too bad. The regions aren't too bad, not to mention the divergence is super simple. This triple integral should be pretty straightforward. Here it is. So by the divergence theorem, this surface integral is equal to this triple integral of the divergence over that region. We calculated that the divergence was 3y, and now we can iterate the integral, and we get this. Apply FTC2 once, you get this. Apply FTC2 a second time, you get this. Apply FTC2 a third time, you get this, a good old polynomial. We love, love, love polynomials. And then FTC2 a third time, simplify, and we get 184 over 35. So that is the value of this surface integral. That's the flux through that surface by that vector field F. Cool, hooray. All right, so next we proved the divergence theorem, but we only proved it for simple solid regions. But it can actually be proved for regions that are finite unions of simple solid regions, pretty much by using the same proof we did before. You just have to split up the integral using finite additivity, and then add up all those resulting integrals, and you'll get the divergence over surfaces that are unions of simple solid regions. So an example is this. You can kind of think of this egg shape, except imagine you had this egg, but the middle was cut out. It's like an egg, but the yolk is removed, right? Or like a hard-boiled egg, but the yolk is removed. Here, the surface S is going to be a union of these 2 surfaces. The outer surface, it's like the outer surface of the egg, and then the inner surface where you removed the yolk, right? Now, the outward unit normal vectors in this case point in different directions. So on the surface S2, which is this piece, the outward unit normal vector points this way. But on the surface S1, the inside, whoop, the outward unit normal vector points like into the center, right? Into the center. There we go. So that's how we're going to change our outward unit normal vectors. All right, now the boundary of the surface E. So E is the surface that's contained between these two. I'm sorry, E is the region that's contained between these 2 surfaces. The boundary is the union of those two surfaces. So the boundary S is the union of the outside and the inside. There we go. And the outward unit normal vector depends on which surface you're on. So it'll be negative n1 when you're on S2. I'm sorry, what am I saying? Negative n1 when you're on S1, and then n2 when you're on S2. There we go. Basically, just make sure you're going out. That's the key idea. Applying the divergence theorem, we get this nice result. So this is the divergence theorem here, but remember our surface S is a union of these two surfaces. We can split up this double integral using finite additivity. There it is. And then here is our unit normal vectors, depending on which surface we're on. And then that's it. That's it. That's it. All right. Now let's use this to do kind of an interesting example. So we're going to revisit an example that we saw back in section 16.1, this example of an electric field, right? So electrical engineers, you'll see this kind of stuff. Here, the electric charge Q, capital Q, is located at the origin, and this vector x is a position vector. So let's use the divergence theorem to show that the electric flux of E through any closed surface S that encloses the origin is equal to this value. So that's what we're going to do. We're going to show that no matter what, the flux of E through any closed surface, it doesn't matter what closed surface you use, as long as it's containing that charge Q, is going to be this value right here. That's the goal. Now, yeah, exactly. So it's interesting because it says the flux is independent of the surface. So that's kind of a bizarre result, but we're going to prove it mathematically. It's also a bit tricky to think about the question initially because we're not given any specific surface over which to integrate. S is arbitrary, an arbitrary closed surface surrounding the charge Q, right? So let's do this technique that we saw earlier a couple of times. Let's use a tiny sphere, and we'll use that finite additivity result that we just derived. So let S sub A be a tiny sphere of radius A, where A is chosen so that that tiny sphere is contained inside the surface S. So basically choose the radius to be small enough that your sphere is inside of S, kind of like that egg example, right? We're going to let E be the region between the tiny sphere and the arbitrary surface S. Then by the divergence theorem, we get this. And let me say something about this. So here's the divergence theorem and that result that we just derived earlier using finite additivity and those like outward unit normal vectors, right? We get this right here. Now, it turns out that the divergence of this electric field is 0, and we're actually going to prove that in our last activity. I think I say that. Oh yeah, I say that in the next slide, sorry. We're going to prove that this divergence is actually 0, all right? Now, just moving some things around, we end up getting that this surface integral is actually equal to this surface integral, and that's super helpful. Why? Because S sub A is just a tiny sphere. It's easy to integrate over, it's easy to parameterize, whereas the surface S is totally arbitrary, right? Okay. Oh yeah, there it is. So we'll verify that this is actually equal to 0 in our last activity. So I'm looking forward to that. Now the beauty here is we can compute the surface integral over that tiny sphere, which is easy to do. Remember that a normal vector for this sphere is an outward unit normal vector is given by this. Should change that. Outward unit normal vector is given by this. So when we take our electric field E and we dot it with this outward unit normal vector, we get this right here. So here we're taking the dot product of two vectors, the same vector. We're taking the dot product of a vector with itself, which if you remember back from good old chapter 12, almost like the second day of class, I think, this is going to be the length of the vector squared, but it's a unit vector, so its length is 1, and we're just left with this. But also remember that the length of that vector x is a, because we're on a sphere of radius a. So we get this right here. That's it. So this dot product is just equal to this value right here, and that's going to make things super easy. Here we go. Here we go. So this surface integral is equal to the surface integral over that tiny sphere of radius a. We just found that this dot product is equal to this. So it's just a constant multiple, which we can pull out of the double integral. And now we're left with this. And this is just the area of the surface. This is just the area of the surface. And so that's what we get right here. Now, what is the surface area of a sphere of radius a? It's 4 pi a squared. Get a nice cancellation there. And then you're left with 4 pi epsilon q. And voila, behold, the flux through any closed surface that can change, the flux through any closed surface that contains that charge Q is given by this value here. And this is actually a special case of Gauss's law. Cool stuff. Just cool results. So fun. All right, so now let's clarify divergence a little bit. This is going to be similar to the last section. But what we're going to do is we're going to see why divergence is what it is, why it's giving us that like tendency to flow outward through things, right? So here's the setup. Let's suppose that V is a velocity field of, for example, a fluid, and the fluid has a constant density rho. Then F, which we'll say is rho times V, is the rate of flow per unit area, all right? Now pick a point P naught in the fluid and let B sub A be a teeny tiny ball with radius A that's centered at P naught. And just like we saw in the previous section, we can approximate the divergence of F at any point P in that ball by looking at the divergence of F at the center of the ball. So it's the same idea. This is an approximation. The divergence vector here is continuous. So what we're saying is, hey, if you have the ball be tiny enough, then the divergence at any point in that ball is going to be about the same as the divergence at the center of the ball. Just make the ball really, really, really tiny, all right? Okay, now using the divergence theorem, we can approximate the flux over the boundary, which is partial B sub A. So that's the boundary of that ball, B sub A. So this is the divergence theorem, that the surface integral over the boundary of that ball is equal to the triple integral of the divergence inside the ball. And here we're going to approximate the divergence at any point in that ball with the divergence at the center of the ball, like so. But again, this is a constant. So this is a constant, so we can pull it out of the triple integral, and now we just have a constant times the volume of the ball. That's what this triple integral is, the volume of the ball. So there it is, the divergence times the volume of that ball of radius A. And just like we saw with Stokes' theorem, this approximation gets better and better the smaller the radius is. So as the radius shrinks to 0, we get a better approximation. Therefore, we can say that the divergence is equal to this limit right here, this limit. Okay, now take a look at what this is saying. Like take a look at the pieces, kind of like we did before. This is the surface integral. Oh, wait. I have a typo here. Ah, dang, those should be surfaces. There we go. Wait a second. Oh, yeah, sorry, I do have a typo. Let me fix this real quick. This should say partial BA. There you go, partial BA. Yeah, so you're integrating over the surface. This is a double integral over the surface, the sphere, right? So this should also say partial BA. There we go. And what this is doing is this is giving us the explicit connection between the divergence of a vector field at a point and the outward flux through a surface, right? So this is the flux through that tiny ball, the surface of that tiny ball. We're dividing by the volume, and then we're taking the limit. And as long as that limit exists, this is a way of describing the divergence at that point. So this is giving a really good geometric intuition for what we mean when we say a particle has a tendency to flow away or a particle has a tendency to flow toward. That's what this is doing. That's really what it's doing. It's basically saying if you take balls of shrinking radii containing this point, right, then the divergence is basically equal to this limit. It's equal to the limit of the flux over the surface of those balls as they shrink to that point. Right. And so that gives us a nice intuition for what a source and a sink is. So I mentioned these earlier in the course, just to remind you all, what is a source and a sink? Well, if the divergence of a vector field at a point is positive, then the net flow of the vector field is outward near that point P. And we call P a source. It's like things are coming from that point. That's why we call it a source. Now, if the divergence of a vector field F at a point P is negative, then the flow is inward. Things are flowing inward to P, and we call that a sink, which makes sense, right? Think about a sink, like it's actually flowing into the sink, right? That's the idea. Okay, then let's see what else is left. I guess that is it. So this is the end. Congratulations. You've now completed Calculus 3. There's, oh my gosh, so much more to learn, so much more to learn. So I hope you don't stop here. Just remember, like I tell my students all the time, there is no highest math class. There's no highest math class. It goes on and on and on. It's just like a rabbit hole, and you decide when you want to stop going down the rabbit hole. So I hope you don't stop here. There's just so much more to learn. But still, congratulations. You got to give yourself a pat on the back just for even getting to this point. And I like to leave you with this quote from one of my favorite mathematicians, George Cantor, which is that the essence of mathematics lies entirely in its freedom. So I hope you take that to heart and explore. Oh, but wait, I think there is one last thing. What's that at the end? Let's play. All right, let's play. We got one more activity to do, and then that is it. All right. So, man, I guess this is the end. I will see you all in class. Thank you all again for watching and listening. Big hugs all around, high fives. Yeah, thank you for going on this journey with me. If you ever have questions, let me know, and I'll be happy to talk to you. Okay? All right. I guess I'll stop rambling here. I'll see you all later. Take care, everyone.